Well, hello ELC 3338. This is Dr. Keith Schubert, and this is going to be one of my penance videos on cash for having to go away on a trip here. So, as I mentioned in class, what I'm going to do is I'm going to talk a little bit, walk through some sample calculation problems. We'll start off, this first one, we'll do a fairly straightforward problem. We're going to assume that we have a computer as we did in class. I'm going to give a little more detail on some of the breakup here because there is a difference between loads and stores as they go in. When we first start off, I'll just leave loads and stores the same. So at the moment we'll consider loads to be 20% of all operations. We can put this in as, we'll see if that's fitting in. Okay, it looks pretty good. Frequency of a load, we're going to make 0.2. And for a store, we'll make 0.05. Just to note, this is fairly reasonable numbers for them. You tend to load more data than you store. And if you think about that, there's some logic to it. You often will have to get a bunch of different values to be able to calculate one thing. So loads tend to be somewhere in that nature of, say, 3 to 5 times the amount that there are stores. We're going to assume for the moment that our miss rate is going to be somewhere around, let's say, 0.004. So, a little bit, this is actually a fairly good miss rate as it's going in, but we'll start off with a fairly low number just to get a decent calculation off it. Particularly if we're dealing with a fairly decent sized cache, that is achievable. So usually we won't do that in one layer, as I mentioned in class, because in order to get the miss rate down, you usually need a bigger cache, but bigger caches are slower for the access time. So what we'll start off here is we'll take a look at the access time for our cache, and we will set that, let's say, at 3 cycles to access it. And let's see, we need to have whatever our penalty is if you miss. So the penalty, that would be, in our case, we said we're just going to deal with one level of cache. So we'll assume it's somewhere around 50 nanoseconds for a 3 gigahertz clock. That means we're going to deal with about 150 cycles worth of penalty. So that gives us kind of our number breakdown. Now CPI, if you recall, this is for the overall. It's a base cost of 1. Now, in addition to that 1, you have to add in the sum of whatever the fraction is times the penalties. Now, in our case, first time through, loads and stores are the same. So the fraction of time we're going to hit this is any time there's a memory op, so that's going to be a quarter. So that'd be 1 plus 1/4. That's the fraction, the sum of these two. Now, what we pay as a penalty is anytime that happens, we have to access cache. Excuse me. Spring allergies. All right. So we have to pay our access time. And I do not know why I wrote a 5 down when it says 3. Well, there you go. So we pay our access time of 3, but then that penalty is only to access it. There's a chance I could miss. So my miss rate, 0.004. And that fraction of the time of this 1/4, I have to pay 150 cycles. Let me check and see if that's still in frame. Okay, it is, so good. Now, what we want to do at that point, right, is think about this in terms, I could actually split. Now, I tend to like it this way, where you can see, a quarter is memory operations, access plus, well, there's another fraction times this. if you prefer to think of them as straight here, because you could say, well, this is nested, it is, you could use distributive property just as a note to you. So you'd have a quarter times this 0.04, and that becomes the amount of time that you hit the RAM penalty. So this could be written, if you want to be very strict purist, as 1/4 times 3 plus a new fraction, which is 1/4 times 0.004, and then that is times a penalty of 150. Now, I wouldn't actually do this in a straight operation. This is really just to show you I could write this as frequency times penalties as a sum, right? Frequency 1/4 times penalty of 3. You pay that one all the time. Every time there's a memory op. For this one, memory ops only 4/1000ths of the time of all memory ops. You end up paying that one. So, it just gives you an option of how you can consider running on this. Now, if we were to take this and multiply them out, right, 150 times 0.004 plus 3 times 1/4 is 0.9. So this ends up plus 1, giving me a CPI of 1.9. So that gives me an initial penalty, or what the CPI penalty cost is going to be. Now, that's still pretty hefty if you think about it. That means, in essence, from an ideal system at 1, I'm almost taking twice as long just because of the memory ops, and that's with cache in there. Now remember, if I don't have any cache at all, I'm going to be paying a significantly bigger cost. I'm going to, on 1/4 of all operations, be paying that 150. And that is just, way too much. So let's consider some other things we could do, but particularly take a look at this difference between loads and stores. Now, one of the things that I can do for loads and stores is I can note for the fact, for a load, I need the data. So let me kind of break this one down. If I'm a program running and I'm saying, let's do a load, I'm saying I need the piece of data from memory to continue my calculations. There's no way I can continue without that data. Whereas if I'm doing a store, I'm saying I'm done with this piece of data, file it for me. I don't actually need you to, I don't need to have it happen before I keep on going. I can allow memory to store it while I am doing other things, because I don't need it to continue. I just need it to happen. But I don't need it to happen in order for me to calculate stuff. It's just, that's a value I want to keep for later. So since there's no time constraints on the stores, what we can do inside of cache is we can actually say, hey, look, you can continue past stores. So the CPU passes out to cache and says, cache, you go take care of this. Now, as a side result of that, for stores, I have to pay an access time. But I don't end up having to pay the miss rate and all the rest of that kinds of stuff that go into it, because the cache will have to deal with that. But the CPU won't be waiting for the cache. Think of it kind of like an assistant. The CPU has a personal assistant called cache, and the CPU says on a store, go file this. The CPU does not need to wait until the assistant comes back and says it's filed in order to take care of things. The CPU would just trust that the assistant's going to do what it was told. On a load, the CPU is waiting for a piece of data and it can't do anything until it gets it. So it's a kind of different scenario that goes on between those two. Now, if I'm under that scenario, then I can do a slightly different calculation, but it saves me a bit of calculations here. So let's see if I got enough room to do that one. CPI under this new scenario. All right, in this case, we still got the 1, but now only 20% of the time do I have to pay the 3 plus 0.004 times 150. And 5% of the time, I have to contact my personal assistant, but I don't have to wait for my personal assistant to do anything. Now, I could technically even split that 3 there up into, say, half, because I don't even have to wait for the assistant to get anything. I just have to pay the access, but I'm not waiting for an answer back. So I could really split that one up and divide that one in half if I wanted to. So, but let's first off just consider what would happen in calculating this as it's going in. Now, for this one, let me just quickly, typing on my computer as we're going on to calculate these. Now, if I calculate that one, this drops down a little bit because this is a tiny smaller. This drops to 1.87. Now, that may seem insignificant, and it is fairly small, but it is an improvement, and it didn't cost us a lot to get it. Now, if I take the next step that's on here, and I split this into 1.5, so that I have a new CPI is equal to 1 plus 0.2 times 3 plus 0.004 times 150 plus 0.05 times 1.5. I only pay the initial cost to send the command off. Typing this into my trusty computer. It helps if I erase the 3 first. This cuts it down to 1.795. Again, this is not a huge improvement that goes on, but think about it from this perspective, right? I've cut it down by a little bit over 0.1. In our industry, every little shaving gives you a performance increase. Now, of the ones that's in here, my biggest cost is right here, right? 3 times 0.2 is 0.6. So if you think about what's going on here, 1.6 of this is entirely controlled by this. So of what I could cut down, I've been able to take the 1.9, 1.6 was fixed, so there's 0.3 that's up for grabs, both here on the your store or your loads, and then there was also the complete stores. I've been able to cut that one down by 1/3, the penalty that was easily grabbable. Now, in order to cut this one down, I'm going to have to change the access time. To change the access time, that's going to affect the miss rate. And this is why what we usually do is we have a first layer, which is small access with a bigger miss rate, and then we have it go to a second layer, which gives us a bigger access time, but it's hidden by the previous layer, and then it has a miss rate that's much smaller, but the miss rate protects me from going out to higher levels. So that's kind of the next thing we'll take a look at. But so here we've calculated 3 different ways of doing these, and we can see the improvements as we move into them. Let's take a look then at that next layer that cuts in here. Now, I've mentioned that I'm not going to require you all to do a big calculation on multi-level caches. That doesn't mean I don't want you to see it. So, let's have you take a look right now for a sec, just what I could do to back up that statement about multi-level cache. So we'll keep our frequency of the load, please pen don't fail on me now, of 0.2. I'm going to ignore the stores for a sec, because as you've seen, they're not hugely important for us. Let's pick a new, kind of like a small cache at front. So it's going to have a miss rate, let's say, let's even kick it up to fairly big, 0.04. Right, so 4% of everything that's going on. But this time my access time is going to be around, let's say, 1 cycle to access it. It's small, it's close, you know, all that kinds of good stuff that's going on. Now, that's miss rate. We're going to call this level 1. Now I'm going to have a miss rate for level 2 cache, and miss rate for my level 2 cache. Now, you know, with everything else that's going on, right, I've got a chance. If it wasn't here, I think of it kind of, remember, locality is our goal. So if you kind of consider this target being this 4% chance, I'm going to get a bigger target at the next layer. But, you know, your miss rate, if you've missed that center part, you're kind of veering off. So it's not necessarily a huge number that's increasing here. Even if I only said this was 0.1, that's going on. Remember, this is 0.1 of these. So the net effect will be this times that. So it's going to be 0.004. So that's, again, getting back to the original number we had before. And our access time for level 2, we're going to kick this one up. This is a bigger cache, so we'll let this one hit, let's even say 5 cycles as we're going in. And then, of course, RAM is going to cost us, say, 150. Now, in this case, what we've got our CPI is always going to be our ideal one, plus 20% of the time we're going to have to pay the load. Every time on a load I have to access. That's going to be the 1. And 4% of that time I'm going to have to go to the next level down. All right, so this is level 1, level 2. So 4% of the time I have to come down here, which means I pay the access time of 5. And in addition, hitting this, 10% of that time I have to go to the next level below, which is 150. Now the 150 is sheltered through quite a bit of layers on here, each time giving me a little bit more protection as it goes. Now in this case, you know, let me just type this into trusty old MATLAB here. All right, so I got times 0.2 times 1 plus 0.04 times, we've got 5 plus 0.1 times 150. And this works out to be 1.36. So you notice it's a huge improvement by doing the multi-level cache, where I've got a small one that doesn't have such an impressive hit rate, but it's that 0.04 directly on this 5 here is not a big number. That's 0.2. So most of this is actually coming from, you know, here and this number, right? So, you know, I got 0.2 times, 0.2 times 0.2, that is 0.04. So it's not a significant number. This does not affect me much. So I can afford to have a big cache with a larger access time. I can even make that bigger without too much of a penalty. The one that's causing my biggest penalty is still this access of 1 cycle. I got 1 cycle, right, times 0.2. That's 0.2 of this. So over half of this is just talking to level 1 cache. So the smaller I make level 1 cache, so that this access penalty goes down, because now it's closer, it's faster, whatever I can do to benefit it will cut this number down bigger than anything else. And you've seen from our previous one, being able to cut that down has cut me from, say, like a 0.9. Even though the net effect for this far out level, 0.1 times 0.04, is the same as I had originally, hiding the 150, the biggest effect was gained by making that small. That's why the multi-level cache works so nicely. So in any case, we've walked through 4 different CPI examples. Hopefully this gives you some help, and I'll consider looking at doing a couple other videos on here as well. We'll see what type of examples will be good ones. So hopefully this helps so far, and watch for some more coming out. Have a good day. Bye.